How's it going, ladies and gentlemen? Mr. Donahue here again. This time we're going to take a look at enthalpy. So our objectives will be to describe what enthalpy is and describe endothermic and exothermic processes. So this is one of the topics where I think it's easier just to start with where we're going to end up with. So what we're going to end up knowing is enthalpy, H, is the internal energy and the pressure volume work of a system. So mathematically expressed as this: H, enthalpy, equals the internal energy E plus the pressure times the volume of the system. So changes in enthalpy at a constant pressure. Well, that means our P isn't changing. So that means our change in enthalpy is going to be equal to our change in internal energy plus the pressure times the change in volume. With me so far, I hope. So when we are at a constant pressure, it changes the P delta V part of the equation. The P delta V part is usually so small compared to the delta E that we can just kind of equate delta E with the delta H. So we can use delta H as an approximate for our change in internal energy of the system when it's at constant pressure. So all right, now let's start for real. Enthalpy accounts for the heat flow and chemical changes occurring at constant pressure when no forms of work are performed other than pressure volume work. Well, what the heck is pressure volume work? Great question. Pressure volume work. So P is for pressure, V is for volume. So changes in pressure and changes in volume of a system result in work being done. So here you can see a little example of I'm dropping magnesium into 6 molar hydrochloric acid, and it's producing hydrogen gas and making magnesium chloride. But you can see all the bubbles. When it drops in, you can see that there's a gas being formed. How's that gas doing work? Mr. Donahue, it's just looking like you're making a gas, so what? Well, the H2 gas must push away the rest of the atmosphere as it's being created. It needs to find space for itself in this universe, all right? So that means it's got to do work. It's got to push away the atmosphere and the air that's in that tube in order to find a home for its own, you know? So if we sealed it with a movable piston, you could see it doing work, right? We'd add the magnesium to it and we'd start forming bubbles, and those bubbles would push that piston up. And because we're forcing that, we have a force, we have a distance, we have work being done. All right? So that's pressure volume work. All right? Mathematically represented as W work equals negative P times delta V. Why is it negative P? Because when we're talking about changes in volume, right? If the volume of a system increases, the work being done on the system is negative. The system is doing the work, right? If the volume goes up. So meaning if the system does work on its surroundings, the delta V is going to be positive, but we want the work to be negative because the system is losing that energy. So if it does this, well, the energy went down because it was doing work. So that's why we have this negative there, right? If volume's going up and pressure is staying the same, we need to have this negative sign to show that when the volume goes up, the system is doing work and it's losing energy, right? The internal energy would decrease. Now, if the volume were to decrease and go the opposite way, there's work being done on the system. So it's positive. So think about if this was a syringe and you had to compress it. Well, you're pushing on it. You're doing work to that system. Well, the internal energy of that system is going to go up. So yeah. All right, enthalpy. Another globe with an arrow on it. What's that all about? Well, enthalpy accounts for heat flow and chemical changes occurring at constant pressure with no forms of work except for PV work, right? So H equals E plus PV. Enthalpy equals internal energy plus the pressure times the volume. E is a state function. P is a state function. V is a state function. None of those things matter how you got there. They describe being there. They only depend on that state. Well, if H is made up of all state functions, H is also its state function. Enthalpy is a state function. So changes in enthalpy are also state functions. Delta H is going to equal the change in, or delta E plus PV. At constant pressure, which is true for what most of the stuff we do. Most of the time we're not dealing with like air sealed things where pressures are changing. So most of what we do in the lab will be at a constant pressure. It's like, atmospheric pressure. we get an equation that looks like this. Delta H equals delta E plus P delta V, right? The P doesn't change, so it's just P. We also know that delta E is equal to Q plus W. We also know that negative W equals, we know the pressure times the change in volume equals the negative work. So if we were to substitute these in to this equation, what do we end up with? Well, we end up with the change in enthalpy equals the heat exchange Q at a constant pressure, which is why there's a subscript P, plus W from this, that's the delta E, minus W, which is the P delta V. And then, hey, look what happens to these things. Boop, boop. The W's cancel out. And we're left with the change in enthalpy equals the heat change, but only when we're working at constant pressure. So yeah, change in enthalpy is a state function. If it's a positive value, it's an endothermic process where heat is being absorbed by the system. And if it's negative, it's an exothermic process where heat is being released or evolved by the system. Well, so let's do a little practice. Do we got a positive or negative value? I don't know why I put C here. It should be delta H. Positive or negative? Here's some scenarios. Test what you know. Try it out. Pause it, then resume. All right, boiling water. Positive delta H. The water is absorbing the heat. You're adding the heat to the water to get it to boil. So it's a positive delta H. Melting ice. Well, the ice, you have to remove heat from the water to... Oh, wait, that's to make ice. No. To melt ice, you got to put heat into it. So that's also a positive delta H. Combustion of propane. Well, I know it always gets really hot when I'm at the grill cooking with my propane. It's because the propane is releasing a bunch of heat. So it's going to be a negative delta H. And hanging up your clothes. Well, I know that they start with a certain amount of energy down here, and then I got to hang them up into the closet. And I know if I do that long enough, I'll be breaking a sweat. All right, because I have to put in the energy to hang up those clothes. All right, summarize. Can you describe what enthalpy is and describe endothermic and exothermic processes? I hope so. Okay, bye.